In this video, I'm going to introduce the Hadoop Distributed File System. So what is the Hadoop Distributed File System, or HDFS? It's a file system that's been modeled after the Google file system, or GFS. In this file system, there is a single common cluster-wide namespace that is typically common with distributed file systems. The Hadoop Distributed File System and the Google file system both have the ability to chunk and store large files. And by large files, these could be single files that are terabytes or even possibly petabytes in size. These file systems have support for the MapReduce programming model and others, and we'll look into that in detail very shortly. They support streaming data access. So unlike distributed file systems like AFS, where you have to copy an entire file locally to the client before you're able to access it, systems such as HDFS and GFS allow for data to be streamed to the client so that the client can start operating on the data as soon as it receives a few bytes or a few blocks of the file. And finally, both these file systems, the HDFS and GFS, assume that you're running on commodity hardware that is prone to failures, especially at scale. So they have to ensure high availability via replication. Now, Hadoop Distributed File System, or HDFS, is actually part of the Hadoop ecosystem. It's the underlying file system for the Hadoop family of tools and services. So we have HDFS, and we have some sort of cluster coordination framework. In Hadoop 1.0, it was just the MapReduce scheduler, but now there is a common scheduler known as Yarn. And then we have a number of applications that can interact with HDFS either through the Yarn or MapReduce framework or directly using API calls into HDFS. This includes MapReduce programs, higher level languages such as Pig and Hive, Apache Spark, Apache Storm, and HBase. Now, a primary difference between the Google file system and the Hadoop Distributed File System is that the Google file system does support, in some sense, file writes, but it's not optimized for them. Earlier versions of HDFS were completely immutable. That is, when you open a file, you can only open an existing file for reading. If you're opening a file to write, it must be a unique, non-existent file. Later versions of HDFS supported the idea of appenders, but in general, HDFS sort of assumes your workload to be immutable. That is, files that have once been written to disk using the HDFS file system will not be opened for editing later on. You can write a new version of the file, but technically you're not allowed to modify existing files. Okay, so let's take a quick look at the HDFS architecture. Now, there are two primary types of nodes in HDFS. We have HDFS name nodes. Now, the name nodes are the nodes that contain the file system metadata, that is the entire file system tree and names and directories and things like that. And then we have HDFS data nodes. The data nodes are the nodes that contain the actual blocks of data that need to be stored in the file system. So if you want to think of it in another way, the name node contains the directory of all of the data nodes as well as all of the chunks that are located on each data node, as well as which chunks belong to which files in the entire file system tree. Clients in HDFS interact in the following manner. The clients first contact the name node to gather the metadata about a file. So if a client wants to open file A, it basically contacts the name node, asks the name node for the whereabouts of file A, and gets a list of data nodes as well as chunk locations from the name node. The client can then read the individual blocks from the data nodes. Now, it's important to note that the client, once it is resolved the metadata from the name node, it does not interact with the name node. It can directly read blocks off of the data nodes once it knows their individual locations. You can see a second client that's also writing data, and also data can be read and written into multiple racks, and we will see the strategies that HDFS employs and how it places these blocks very shortly. HDFS also assumes this cluster topology to be the data center fat tree style topology. So basically what we have is we have individual switches in individual racks. These switches are connected to individual nodes which have the disks on board, and then all of the racks are connected through a higher level switch. And in fact, this could be multiple levels, in fact. But it basically assumes that your network is wired in this tree topology. This is optimized for lower level traffic. So HDFS assumes that this is the kind of topology that exists in the cluster, and therefore tries to minimize transfers that exist between nodes and between racks. So if a client is trying to read some data on the same node as 1, and the client is actually running in node 1, if the block exists in node 1, node 3, node 6, the metadata will actually say, hey, you can read the block from node 1 because it's closest to you. Similarly, if you want to transfer data from between nodes, it'll point you to the node that is closest to you in this tree, rather than pointing to you to some node that is on another rack, to minimize inter-rack transfers. In fact, HDFS also exposes the location of data blocks to certain applications. So, a MapReduce scheduler that is scheduling map and reduce tasks, if the data is sitting in HDFS, the metadata resolver, that is the name node, will actually expose the block locations to the clients. So the MapReduce scheduler can actually schedule the tasks closest to the nodes that have the actual data blocks. And this is kind of interesting because the distributed file systems typically don't do this. They strive for sort of this location transparency, but in HDFS and GFS it's fully aware of the locations and makes that information available to the client if the client needs it.